Well, good afternoon and a very warm welcome to our final session in this bite-sized corrosion series on maritime corrosion. We hope that by the end of today, when you leave us, you'll be eager to continue your journey in understanding corrosion just that little bit more. During this series on maritime corrosion, we've had some fascinating discussions about naval vessels, challenges with corrosion on the vessels and combating that. And we've also taken a look at the difficulties and interesting experiences that occur when you're diving to do inspections about corrosion underwater. Now, today we're going to be heading a little further north, and we really welcome Frances Bradfield to the microphone. Frances is based in Denmark, where much of her time is devoted to preventing corrosion in offshore wind farms. So, warm welcome, Frances.
Thanks, Vanessa. It's nice to be back. I was trying to think when it was, about a year ago, a year and a half ago, doing
Exactly.
some other stuff on ECDA for pipelines. But this, as you say, is my more day-to-day nowadays. I moved from South Africa and pipelines into Denmark and offshore wind farms. Same, but different. So I'm excited to chat about it.
Well, that's what we're wanting to find a little bit more about. Now, my knowledge of wind farms is very limited to the few wind turbines we see along the coast here in South Africa. So can you give us a quick crash course in some terminology? What is a wind farm, where they're located, and what we're going to be looking at?
It's a good one because I find myself saying a lot of things like monopile and jacket, and it all sounds very scary and different. And I had to Google it on my first day many times, but I'll just give you a quick, very small slide. When we're talking about offshore wind, we have foundations that are by themselves, and you have one foundation for every offshore wind turbine, the big windmill that you see out in the sea, and we have to fix them to the bottom in some way. The most common types here are monopiles, which one pile, basically a pipe that you drive down into the seabed. As you can see, it's on the left-hand side. And then we have something that resembles a traditional offshore oil and gas platform called a jacket structure, where we have pre-installed piles or post-installed piles and a jacket structure that is then laid down on top and fixed to these piles. And once we're finished installing this structure on a jacket, you bolt the wind turbine directly onto this main structure. But for a monopile itself, you smash down the monopile through the soil to the correct depth. And then in general, we have what we call a transition piece, which is a separate section that is lowered on top and bolted to the monopile. And inside this, we have all of the equipment for the transformer and the cabling and for the cathodic protection, which we'll talk about later. And onto this transition piece, we bolt our wind turbine tower.
Thank you. That's certainly given me a quick education in wind farms. Now, obviously, that structure, that monopile, if we contain our discussion to that initially, will find itself in various environments. You've got some deep into the seabed, you've got some in that sort of muddy interzone, you've got some in the water, some in the splash zone. How do we stop corrosion?
So it is a bit of an interesting animal. I do liken it to a pipeline crossing across a country where you have a swamp and a desert and a bit of above ground and a power station or something like that, wherever you have it. But each individual zone has its own challenges. We're lucky that the first bit, if we go from the bottom up, is very far down and has oxygen deprivation. So we can assume that there's no corrosion going on there. So that makes our job very easy. We smash it down and we forget about it, and it continues its life very quietly down below the seabed there. But as we come up towards the interface between the seabed and the sea, that is probably our most critical area. I think that you have had these discussions probably about piling as well when you spoke with the divers, and where we're seeing the most corrosion with this accelerated low water corrosion at this interface because of the differences between oxygenation and nutrients and everything, and different maybe bacterial colonies that can grow. We have this big question mark zone. So I think we can get into that in a little bit because it's a little bit more complicated. But when we get into the submerged zone, in general, monopiles or jackets, we can go anywhere up to 70 meters in depth, which is really deep. And that means that even within the submerged zone, we have different characteristics of the water column that surrounds our structure. But in general, that is protected by cathodic protection and coating, or just cathodic protection, especially if you're heading off into the east, where they don't want to spend money on fabrication. So they prefer to throw cathodic protection at the problem.
Power at it. Okay.
Also fine. It works. And then we have our second transition zone, which is probably fatigue-wise. And I say fatigue, I'm not a structural engineer, but my structural engineers are always complaining at me that this is a place that we really need to worry about. So this is one of our big things. It's called the splash zone. So in the tidal zone, and where we can expect the water to be hitting up against the structure, as you can imagine would happen offshore. This is where we end up with the highest rates of corrosion, and we need to protect that by coating, because in the upper section of that, our cathodic protection is no longer effective.
Yeah.
So we need a really good coating and then corrosion allowance to make up for the rest of the lifetime. And when we start saying stuff like corrosion allowance and free corrosion, the structural engineers start yapping again, and they like it very, very little. So we need to come up with good ways of maybe extending maintenance a little bit, which can be difficult. As you can imagine, nobody wants to paint something while being splashed with a wave and hanging off a rope. So it's dangerous, it's expensive, and sometimes not even possible. But we can do a lot with these new, really good coatings. Once we get above that level, we have maintainable structure. It can be difficult to maintain, but it's still probably possible. And that's generally what you see sticking out the top, which will be a nice yellow color so that everybody can see it. Although I have some very interesting videos that show that even when they are bright yellow, ships just go straight in.
Yeah, that's a bit scary. Just rolling back just a quick little bit, do they construct these monopiles or any of these offshore structures out of conventional normal mild steels, or are they going to the fancier steels? And if they are, we always say those should be used with caution. So I presume they've done some rigorous testing on them.
So in general, we use steel 355, which is a higher strength steel, but it's not one of those super fancy ones, I imagine. I think, again, I'm not a structural engineer, but there are reasons why we need to use sometimes less strong steels to deal with the impact driving, especially for a monopile. It's an extremely fatigue heavy process.
I presume it's like a big hammer, just whacking down on it. It's a massive
hammer. You're dealing, and these monopiles, to give you an idea of scale, the largest one that we have designed recently is 13-meter diameter, which is half of a swimming pool. And you have this massive thing being smashed in by a huge hammer. And the monopiles themselves are about 100 to 120 meters long. So this whole thing is a huge process, and it looks very small when you see them far away. But if you see them up close, it's very, very impressive. So the steel themselves, even the self-weight, when these structures are lying on their side, they do become ovular because they compress themselves. So the material of construction is probably a mixture of both these super high strength steels and conventional mild steels, or something in the middle of that. But we need to make sure that there is zero corrosion on this, because the fatigue that implies with any free corrosion is design driving and can make your whole structure not feasible. So our job is really to help the structural engineers make a good lean design without having to overcompensate on corrosion allowance or fatigue considerations due to corrosion.
Now, we were talking about the use of sacrificial anodes recently, and something we don't always take into account is that if you're putting sacrificial material onto your pile, that's very heavy, so that will also impact on its usefulness. But sacrificial anodes are also being maybe frowned on for other reasons. Shall we chat about that briefly?
So I think traditional oil and gas platforms, like those jackets that we showed with the very complicated structure, those in general have galvanic anodes welded to them, nicely distributed. It gives a very good even protection all over. However, we have got massive issues, especially in German and French waters, but the largest political issues are actually in the US, where the fisheries have come up and said absolutely not, because there is a huge concern of heavy metal buildup in the water. So zinc is a big anyway. We no longer use zinc externally, even where you use galvanic anodes. We have to use them internally because of acidification, and I'm not sure we want to get into that right now. But having metal ions dissolved into the ocean for one foundation, to give you an idea of scale, one of the latest wind farms that I've just done has got 176 individual foundations. And if we were to have done, it's a US project, if we were to have done that with galvanic anodes, we would have had 45 tons of aluminium per foundation, and that all would have been dissolved into the sea. So environmentally, it's not the lightest footprint. So you don't have that emission of ions to the sea. Of course, you have loss of current from your wind turbine, so it's a little bit less green, but you're not actually emitting a toxin on site in the ocean. So it makes it a little bit lighter.
How do they power the ICCP system? And I was assuming that you draw it from the power that you're generating on the monopile itself. But probably some quite clever electrical engineering that happens there too.
Well, I think you don't have a rectifier. You're making DC power, so you don't need that, but you do have a transformer. And what we do is from the main transform unit of the WTG, we have a small siphon that comes off the siphon of the power into our own power unit for our ICCP systems. Usually we have one for external and internal if it's a monopile, because there's water on the inside. But if we just look at the external side, you're looking at the requirement for it's not negligible, the amount of power you need. You can calculate the number of them, and so it does have a cost on the power production from the wind turbine. But if you're looking at a 15 megawatt turbine, it's virtually, insignificant over the full lifetime. But we do.
That's really interesting. And then I presume strategic location of your anodes will be what determines how much you're drawing for your mud level portion compared with the midsection, compared with the splash zone?
Correct. So we have a challenge when it comes to monopiles, and that is when we drive the monopile in, we cannot have any attachments. So we're not smashing it in with anodes connected. We can't do that. We have to have a naked, nice, sexy monopile with nothing on, smashing it down to make sure that we don't have any fatigue issues. And that means that when we want to put cathodic protection on, we have to do it after that monopile has been installed. That is now generally done when we attach the anodes to the transition piece, that piece that goes on top of our monopile, and that we lower down and bolt. So there's no fatigue driving on that. And that has got all the cables already installed onshore and brought offshore. And then once we've bolted it, of course, it's earthed as well. But the power is then sent through the transition piece into the monopile through these anodes that stick out like lollipops, basically, all the way around the side. But that does mean that if you have a 70-meter water depth, you have current coming out the top, and you need to get some relevant potential that you need for whether we're going to say if it's 900, 800, 1100. Again, we can talk about criteria, and maybe it's another topic. It's far away, and we need to make sure that we can get that amount of current out to down here without overprotecting, which means we're pushing ourselves in the Paul-Bert diagram, if everyone knows what that is. We're pushing ourselves above the hydrogen line, and we are producing hydrogen at the cathode, so at the transition piece, and we end up with hydrogen-induced cracking or stress corrosion cracking, which is it's a big trade-off, and we struggle a lot on these really big monopiles to do that, especially in the North Sea and the Baltic Sea, where the salinity of the sea is so low because the temperature of the sea is so cold.
Yes, one doesn't think of all of the ramifications when you're looking at it from the outside. Obviously, when you're involved in it, you're encountering that all the time. But I hadn't thought about the fact that the sea isn't as salty.
No.
And
In
so
fact, I
your
went for a swim
conductivity
the
is
other
good.
day and I didn't even need a shower to get the salt off afterwards. It's very cold.
I wouldn't have gone for a swim. It's way too cold for me. Frances, have you ever thought about lowering anodes from your transition piece geographically to sort of suspend them like strings hanging down, weighted strings or something?
Yeah, so we could do that. The velocities that you see of the water current around the monopile, for example, or even around the jack, anything hanging is not going to work. But one of the things that we have done with ICCP, but it comes from the original galvanic anodes, is we lower a cage down. So you have the monopile, which you smash in, and before you put your transition piece on, you put a belt, a skirt down, you lower that down and connect it onto some kind of trunnion or support that you've got, which again, the structural engineers don't like, because when you're smashing in the monopile, it gives some issues with your fatigue on your monopile. But if you do have those, you can slip down a ring of anodes, whether they're ICCP or galvanic anodes, and you can have them closer to the mudline. So that's good. The issue with that kind of thing is it's another lift. So you've installed your monopile. Now you need to lift up a cage and put it down. And then you need to put your transition piece on. So it's another lift, which doubles the installation time of your foundation. And they say something like 1 hour offshore is just insane amounts of money. You're talking hundreds of thousands of euros per day to have an installation vessel offshore. And so we get a lot of pressure to minimize the complexity of the installation.
Yeah, there's
We don't
always that
like it.
trade-off. No. And again, another consideration of the cost of corrosion and the cost of its protection, which needs, as you say, it's a trade-off and a balancing act. And in many ways, something that perhaps we will never know is right or wrong, because these have a 20 or 50-year design life. And, certainly I'll be gone by then.
Yeah. Well, at least retired, Vanessa. Let's not hope gone.
Yeah.
But well, actually, I've just been asked to design a wind farm with a lifetime of 60 years operation. And so I thought, well, I'll probably be retired by then and it won't be my problem. But there's huge unknowns, so we don't know. But
Yes.
we get this big issue between the project saying CapEx, capital expenditure. They want to keep that to a minimum, and they pretty much cover their eyes to what it's going to cost operationally later on. So we, as consultants, need to show them, yes, it might be cheaper now, but in 20 years' time, you're going to have a huge problem.
And the but may also include safety issues, which obviously the cost of life is immeasurable. So that's also something. Now, yesterday in our discussion with Fulufelo Sitole, we were talking about the buildup of biofilm and talking about how important it is to get the cathodic protection working as quickly as possible. Now, if you're talking about delays in timing to bash in your pile and then add on the superstructures and then only get the power to give you cathodic protection, do we have any idea what impact that has on the formation of biofilm and the risk of cathodic protection possibly not working?
So I think a lot of these wind farms are installed in the colder climates, which is really great because everything takes a little bit longer to grow when it's minus 100. So that is really good. So our experience from offshore wind as it is now is that we have not seen huge marine growth within that time. However, with the growth now of the Taiwanese, Chinese, Korean, and Japanese wind markets, we are starting to see that they do have significant marine growth in the upper sort of splash zone, let's call it, area, where you can imagine you've got sort of green algae forming. And I can imagine that that would be problematic. We, as I say, we rely heavily on the assumption that the coating we have on our structure is pretty much undamaged at that beginning stage, and that if we do have marine growth, we have a buffer to the base steel. But we would need to sort of make sure, especially in that lower zone in the interzone between the buried zone and the submerged zone, that we don't have anything like a hard marine growth biofilm kind of thing growing up. On that, actually, we saw some interesting photos from site of piles that for jacket structure that had been installed 3 years previously, and they did an ROV, a remote operated vehicle inspection with a camera, and there was marine growth in that zone, but it was not hard marine growth, so there was no barnacles, no oysters, none of that. There were quite a lot of seaweeds, but those are quite easily removed, even just with an ROV and a small brush. But I think if you were to have a whole colony of oysters or something equally delicious growing on your monopile, we may need to remove those before we can be sure that the CP is working below them.
Frances, another thing that has just come to mind is when you're talking about your jacket structures and not being allowed to use sacrificial anodes, those shapes are quite a challenge when it comes to impressed current cathodic protection. How do you design something
with many wrinkles? Yeah, many wrinkles and a lot of gray hair. I'm still trying to see. It's not our favorite thing. Our go-to, if we had our way, would be galvanic anodes for jackets and impressed current for monopiles. They work really well on those two things. But it is possible. Basically, when we have impressed current, especially on something like a complicated structure, like a jacket, we rely heavily on computer simulations to prove that we've got proper cathodic protection in those complicated geometries. Because of all the shielding and the way we have to have the stick outs and the angles and making sure everything is well covered, we cannot do it analytically. So that's another good thing to mention. Right now, we're not designing any impressed current systems without computer simulation as a backup. Galvanic anodes you can still get away with if you know what you're doing, but even then, when you've got these very long piles, you need to make sure that you're getting sufficient current spread down to protect the piles themselves. And that is really only possible with computer simulation, because your assumptions that you've got evenly distributed current are not valid as soon as you move away from the structure.
Gosh, Frances, this is a fascinating discussion, and we could go on for hours, which unfortunately we don't have.
I did warn Vanessa, everybody. I said it's a very broad subject.
And fascinating, really, really interesting. And I hope that our audience has found it as interesting as I have. And Frances, thank you. And I'm certain that we will have you back to have a full series on discussions about these offshore structures, especially as they're becoming kind of the new scenario. I think we're going to see a lot more offshore structures, and certainly here we've got less experience down in the south. I imagine there'll be a lot of structural concerns with some of the turbulence of our waters down here. But thank you so much for giving us so much food for thought in terms of corrosion and combating it. If discussions related to corrosion are new to you, I would like to invite you to learn some of the fundamentals about corrosion. And you can do that with our online course on conquering corrosion. Thank you for joining us. Goodbye.